Thank you so much. It's nice to be back. I feel like it's been like 24 hours. James, do you have any idea what I got in store for you today?
No. There's been a lot of people telling me that they've been part of test runs, but no one has spoiled. I have no idea what's about to happen.
Okay, so what's going to happen is the Rust web app that I threw together is going to collapse under the sheer amount of people tuning in, I think.
The number's going up.
The number is going up, which is normally good. So I wanted to do something a little special for today, and I thought I would build a quiz system to use just to quiz you on your knowledge of compiler optimizations in Rust.
Oh, no. Oh, no.
No? You said you wanted to keep the surprise.
Yep. I'm seeing that 70, and that 1 of 70 is making me a little worried right now.
No, it's fine. Okay. We'll be quick. So what's really fun is that you're playing against everyone else. You can actually, take your phone and join if you want to, but we can just like keep track of your points.
Well, yeah, someone will. Someone
will. Please, someone. Thank you.
So I'm playing against actual compiler developers, is what you're telling me.
You are.
Okay, excellent.
So this has been play tested like 7 different times in one-on-one sessions, so that I have explanations for everything that happens here.
Good.
And it has started several fights as well.
So I'm about to learn a lot of things, aren't I?
Because things happen and people disagree that those things might happen, right?
Okay.
Sometimes the answer is like, it does, but it really shouldn't, right?
Okay.
Are you sufficiently hyped? Do you need more?
Oh, I'm as ready as I'm going to be.
Okay, so here are the rules of the game.
Okay.
We're playing on Rust 190, latest stable, with the LLVM backend. I wanted to test like the GCC backend, and I wanted to test crane lift, but I did not have time.
Okay.
We're playing on the x86-64 Linux because I feel like that's what people know the most in terms of assembly.
Fair.
I'm still getting used to ARM64 assembly, and we're playing on like default release profile, no CPU-specific optimizations or weird LLVM flags. Okay.
Okay.
There's no tricks. There's no tricks in this whole presentation. Let's start really simple. We have warm-up questions here.
Excellent.
Does this Rust code compile down on x86-64 Linux to something that uses the div instruction?
I'd say probably not. It's probably a right shift by 1.
Mm-hmm. Okay, so because this is a warm-up question, it doesn't really matter. But for the next questions, what we're going to do is we're going to talk about like our reasoning or where the mind goes, or what this reminds us of, and I'll give like the right answer right off the bat. Otherwise, everybody's going to have the maximum score. Sorry for not making that clear. We have a bunch of votes already. No, this does not use the div instruction.
Okay.
I think this is the first compiler optimization I learned about. It actually, you're right, it does a right shift by 1.
Excellent, excellent.
Now, if you divide by 5, does it use the div instruction?
Divide by 5. I'm going to say yes. There's probably a smarter compiler optimization than this, but usually it's hard because it's not an even power of 2. So I'm going to say yes, it does use the div instruction. Oh, no. We started off on a bad foot.
So this was actually really fun. I added it near the end because I had other, like, I just tested powers of 2 and other things. And it turns out that, no, it just multiplies by this ginormous constant.
This is like the inverse square root thing, where it's just like, we experimentally does. I'm sure there's a very specific reason why this does divide by 5, but I love that number. And then right shift by 66 on a U64?
But the reason it works is because the input register, like for the multiplication, are 64-bit wide, but the output is 128-bit wide.
Yeah.
So that works because now you just make it smaller.
Nice.
This is terrifying, by the way.
I don't think it's going to get better.
Okay, so we've just seen a trick, right, where you can replace pretty much any division with a mul instruction. So this is a different question. It's not does this use the div instruction. This question is does it use the mul instruction? Does it use the same trick we just seen?
Can you divide by U64 max? Doesn't that set like an overflow flag in the processor? Does this not compile, or does it cause some kind of trap? I'm going to guess no, it does not use the mul instruction.
What does it use?
My guess is it might not compile, but I forget if that's
it does compile.
In
it does compile.
Or does it just give you a 0? I'm going to say no, it just gives you a 0.
Close. It doesn't use the mul instruction. It tests if it's equal to max, and if so, that's 1. Otherwise, it's 0.
Fair.
So this is not a question. Everybody can relax. So divisions are right shift, as we've seen. Multiplications are left shift. So multiplying by 256 is actually left shift by 8. And something fun that I noticed is that even multiplying by 255 is left shift by 8, and then just subtract like the one too many x's that we added.
Yeah.
And I started getting nervous about overflows, but actually this works, right? Because it can overflow, and then it can wrap back. It's fine. This is beautiful.
Yeah. Was it rotate with carry? This is where actually x86 is one of my least competent architectures, because I usually do microcontroller things.
Yeah.
And those ones, the only reason I know that a lot of these exist is because a lot of microcontrollers don't have hardware divide, so everything is soft instruction. So if the compiler can do anything to avoid a hardware divide, it will.
True. Well, this is what this whole podcast is about, right? It's about taking both of us out of our comfort zones by hanging out together. So more exposition. This is how small multiplications look like. We can use load effective address, which is great because we get a multiplication, or like addition plus multiplication, and a move at the same time, because the first argument is an RDI, and the return register is rax for integers. However, for multiplication by 2, there's a bunch of different ways to do it. Which one do you think LVM is choosing?
Hey, quick question. What does the LEA instruction do?
Load effective address. So it's doing like an address calculation. So that's why you can, okay, let's go back one slide. That's why you can only do, you can't do like 5 times RDI. It has to be like a multiple of 2. But you can do some additions. It's just computing like an address and then like putting that address somewhere. But not actually loading what's at that address. It's not a move. It's a
add RDI. I'm gonna guess C because is it green already? Did I lose? Oops. So it's A.
Good job. In this case, yes, it is A because that's apparently the shortest one. I think that's the reason. I'm not actually sure about that one.
Darn you, CISC instruction sets.
And I've heard that LLVM can actually pick other ways to encode it if it needs some things to be aligned, like some code to be aligned for looping reasons and stuff. Yeah. Now onto floating points, which everybody loves and are unproblematic in every way. Does Rusty turn dividing by 2 into multiplying by 0.5?
Would it prefer multiplication?
Yeah, because it's more efficient for sure.
Is it?
Yeah, it is.
Then yes, it would.
Yeah, of course. Follow your instincts.
Yes,
like I said, like not everything's a trap, you know. And it does the reverse as well. If you divide by 0.5, it's actually multiplying by 2, which actually goes even further and like just adds XMM0 to itself. In this case, it's both the input and the output register for floating point. So we can use add. It's the most efficient thing. Now, can we transform x divided by 1 to just x?
No, I know there's something in 754 where dividing by 1 is it signaling in some way? I can't remember. I'm going to say no, it does not do this transform.
I'm going to wait a bit. We have votes coming in. It does.
Darn.
But 74 people were wrong with you, so you can feel less alone.
Well, I think some people are going to start listening to my reasoning, and I can be very convincing even when I have
But this is, no, but
who really knows about IEEE 754
Your mind went exactly in the right place. This only works in Rust. In C++, it doesn't, because you're right. Then it could throw a floating point exception if x was nan.
Yeah, right. That makes sense.
Yeah. But by, like in the Rust, I don't know, somewhere in the Rust, you have no idea how much Rust documentation I have read over the past month, okay? Somewhere it is written that, like, no, it's all quiet nans in Rust, and that's it. Can we do this? So dividing by 1 over 4, is it the same as just multiplying by 4? Maths says yes.
Divided by 1. I'm going to say yes, it can. I'm going to try not to read too much into the pattern of the first one's not a gotcha and then the second one's immediately a gotcha. So I'm going to say yes. Yes, it can, because it's a constant transform, and so it can do that.
And you would be right.
Okay.
You would be right. Here's a completely different question.
Oh, no. Because I'm going to say no, because I know 4 happens to be a power of 2, which is easier to express in a floating point, but a 3, I mean, if it's a single digit, then there's no mantissa or whatever to it. So I'm going to say yes, it also can do that.
Yeah? Let's wait till the popular vote agrees with you.
Oh.
Wow. Only 39 believers.
What horrific fact am I about to learn?
So wait, what is this one? I forget this one.
Oh, I feel a little better now.
No. Okay, this one is just that the first thing it does is 1/3, and yeah, it does it has infinite digits, the bits of the synthesizer.
Oh.
And then it's like, oh, we don't have an exact representation for this, so we can't continue constant folding.
That makes sense. Yeah, because one will yeah. Okay.
Yeah, so it does actually. Yeah, we see it's doing a division.
Oh, this is like tricky, like do fixed point operations on floating point numbers kind of thing, isn't it?
It's interesting that it's actually, yeah, the constant is there and it's dividing once, which means it's, whatever. Don't have time for this. So can we replace x divided by 0 with just infinity, which is much faster?
What is Rust's rules about dividing by infinity in a floating point number? No, it can't.
Well, I fucked it up and we already have the answer.
It's my one vote. I was right.
You're right. Why?
I don't know. It's going to be one of those terrible like exception rules of trapping.
There's a finite amount of numbers.
Or does it just not?
You know, there's like 0, -0, infinity, -infinity, all the nans, doesn't matter which.
The variety of nans, yeah.
Yeah, and that's it. That's all the numbers that you have to think about for these questions.
Yeah.
So basically, yeah, if you divide,
yeah,
you can get infinity, you can get -infinity as well, which is not, the optimization didn't give us that. And you can get none if 0 divided by 0 is none, apparently.
Yeah. Can
we do this? Now, we've seen this. This is a repeat. This is just to make sure you're paying attention.
Oh, no, I'm not paying attention.
You're not paying attention?
Divided by 1. What could it do divided by 1? I forget if it could do divide. No, we did multiply by 1 before.
No, we did. No, divided by 1.
Oh, great.
Yeah.
I'm going to say no, it cannot do this transform.
Why not?
Don't ask me to justify my answer.
That's the whole point. That's the whole reason you're here.
Because I wasn't paying attention. There's nothing but fear and adrenaline going on right now.
It's not changing the sign of x. It's not making it infinite or -infinite or none.
0. So it's does it just magically?
And we don't have signaling nans, so it's fine.
Doesn't it just become infinity? But that's not a transform. That's not the transform you're describing. You don't just magically turn it into infinity.
You've lost me. Anyway, the answer is yes. Yes, this is fine. This is absolutely fine. And then here's a completely different question, of course.
What was the answer to the last one? Yes? I'm going to say no to this one. Because we've learned that 3 is a tricky number and that floating points can't do 3s.
You're game theorying this episode. Well, but same reasoning, okay? It's not changing. We're dividing by 0 anyway. So
yeah.
It's going to be...
But you're not asking me if we can elide the divide by 0. You're asking me if we can elide the divide by 3, in which case I'm going to say, no, we cannot elide that divide by 3.
Yeah?
Does it become a different infinity? Some infinities are... No, there's only one.
You're going to need a better explanation than that, James.
No, I got nothing.
No? All right, well, you're right to doubt me.
Yes! Standardized tests.
You're right to doubt me. I actually had no explanation for this one, and I was upset. And I was like, Russ should do it. But I got one. So... the thing that's happening here is that 0 divided by 0 is nan.
Mm-hmm.
And if x is like not 0, but like really small,
it might convert.
And then we divide it by 3, it's going to get like
turn
into 0.
So there are some cases where this becomes infinity, but some cases where it becomes nan. So it has to keep this so it can figure out whether it's what terrible value of float it decides to put in there.
You got it. Moving on. Yeah, so the 3 question marks because I didn't know what was going on until I talked to smarter people. Okay, multiplications now. You know, just relax a bit. Can we turn x times 0 into just 0?
Can you times 0 to 0? I'm going to say yes, it can. Because it feels like that's a thing that it should be able to realize that's 0. But then I'm going to learn something terrible about floating point numbers, that some zeros are not exactly 0. More than the regular floating point.
This one is actually pretty straightforward, right? We have 60 no's. No, you can't.
Oh, because...
I told you, there's only like 7 or 8 categories of numbers you have to worry about.
You're right.
Not using your head, James.
Now, you've been in... Yes, okay, great.
Our favorite number is back again, 3. A very hard number. CPUs hate.
Because if it's infinity, and you times infinity by 3, it stays... If you times nan by 3, you probably get some terrible trap. I'm going to say no because I think that the traps are... But this is Rust and not C. So float can't be nan, so I can't do that. So if it's just infinity times 3, if it's negative infinity times 3, but times 0, I feel like the answer was on the last slide and I forgot it. So I will say no, it cannot do this transform.
You would be right.
Nice. I think I'm learning.
For a similar reason as the other one, which is if it's really big,
yeah,
and then you multiply by 3, then it becomes plus infinity.
That makes sense.
Yep.
Oh no. Fmol fast.
This is not a question. Everybody breathe in, breathe out. This is just to say that there is no way. Several people have listened to me say this and haven't contradicted me. So there's no way to enable fast math globally in Rust.
Yeah.
And I tried, because you can pass LLVM flags, and there is an LLVM flag called fast math.
Yeah.
But it doesn't actually do anything. It doesn't change the code gen.
Oh, really?
But I don't know what the flag is supposed to do. I just know that in Rust, if you pass it, it doesn't actually code gen something different. What you can do is use intrinsics to do fast multiplication, and those assume that it's not infinity, it's not negative infinity, it's not. It is actually 0.
Nice.
Yeah.
I was gonna say I'm familiar with it in GCC because there's some things, but it definitely makes things go fast, and then it makes some things not work.
yeah, for sure. It's very dangerous to enable it globally, and even locally. I don't know. It's time for some jokes.
Does this end the floating point number portion of
yes,
the pod?
It does.
Yes.
James, if you divide your company into 0 parts, what do you get?
Infinity.
No, you get none of your business.
Oh.
Because your company is worth 0, so, you know.
You did ask me what my sense of humor was.
Yeah. If your grandma works on an airport runway, what do you have?
Nanfinity.
No, you have a signaling nan.
Oh.
And finally, why did the JavaScript core team hire a fast food worker?
Negative infinity.
They had prior nan boxing experience.
I want to go to your fast food Indian place. I want to go to your fast food Indian place to get the non-experience.
Sure. We'll see the scores at the end of the game. Don't try to.
Is someone keeping track for me? Has anyone kept track of my score so far?
We clearly requested someone do it, so
we'll have to ask Amanda to do it.
Yeah. All right, more optimizations. Do you think the compiler recognizes the worst possible way to return 0?
While executing, yes, it will. I feel like I've seen this LLVM optimization before.
Okay. Are you sure?
I'm pretty sure.
Let's see what people say.
Because it's divided by 4, which means the upper bound for this is, if for a 64-bit number, is it could max do 64. There's some limit where LLVM will be able to do, like, it will just do the math up to a certain number of steps, and at some point it gives up. And I think 64 is within that bound, but maybe
is that what happens?
I think there is some level of like symbolic execution, or it's probably the wrong term for it, but something like that.
That's terrifying.
But if the answer to this is no, and then later you give me a 32, then I bet you the answer to the 32 is going to be yes. So I'm going to say yes for this.
No. Yes, you're right. It does do this transform.
Okay.
So you can write return 0 like this if you really.
Are you about to give me a U128?
No, not at all. We're going to do an add. We're going to do an add function. This is an ON implementation of add. Do you like it?
Wait, what does? I'm gonna say no, because the bound is much larger on this because we're doing addition and there's not like you know, power of 2 division. So
if your theory was right last slide, then this will be no.
I'm gonna say no, but that doesn't mean there isn't some other trickier optimization that this triggers. So I'm gonna say no.
James of little faith. It does.
Clever compiler developers.
Which is what makes me believe that it's actually proving that it's doing limits.
Yeah.
It's not like actually going through.
There's so
15 quintillion numbers.
Yeah, there's so much of this pattern matching that I've just seen a bunch of them. What are they called? Was it keyhole optimization? Where they go, we've recognized this pattern. This must be this. Therefore, that. And it's like someone's written a proof of like, yes, this must always be the same.
Let's talk about something you have 0 experience with because you work on embedded and it's forbidden. Allocations. Heap allocations, sorry.
Okay.
Does this compile down to return 4? So making a new vec, we're pushing 2 twice, and then we're adding v0 and v1.
I'm going to say yes, because Rust is allowed to elide that, I believe. Like, it's not necessarily required to assume that allocations are side effectful, I think. So I'm going to say yes, it does.
There's people in the audience just like nodding to what you're saying. Yes, yes, it is correct.
It's good that I can't see anyone.
Yeah. However, it doesn't.
Damn it! Wait, why doesn't it?
Because the initial capacity is 0, and then it's growing the vector, and then it has to copy things over. And even though it's 0, like at this point, the compiler just gives up. Is my explanation. Someone can.
I would love. Did you test this with capacity? Then I'm going to say yes.
Thank you.
More confidently than that, yes, though.
But how funny is it that like I have a slide for this? Yes.
What 14 of you in the audience are that confident that Amos is tricky?
Wow. No, this is fine. And you're absolutely right. Like if you have a custom allocator and you install it, you can't rely on like things calling into your allocator because the compiler is allowed to like
You didn't claim that we're using the system allocator. You didn't claim that we're using the system allocator.
That's true, but we are.
Okay.
All right. So we all agree that this allocation is being elided, right?
Yes.
It's being eliminated completely. Therefore, it should be totally fine to allocate.
No, because aren't you not allowed to
5 quintillion, I forget.
Can't
19?
because the allocation size can't be larger than I size max, and if you are allocating, you don't say what type these numbers are, so they must be I32. So if you do with capacity, you're actually doing 4 times the capacity of the system. But a single allocation can't be more than I size, which is half of that. So you're 8 times more than your total max allocation. So I'm going to say ... no.
No, indeed. Good job. So this hits an assert in rawvec.
Yeah.
That's no, that's too much capacity.
Because it can't exceed I size max. Yeah. Even if it was a U8, but since this is an I32 because you haven't specified it, it's going to be 8 times bigger.
So clearly, I just need to take it down like 3 or 4 notches.
4 won't. Well, 4. Okay. But you shifted by 4, so that's dividing by 16.
Yeah.
And you haven't tricked with any of the numbers, so they're 4. And I said it was 8, and divided by 4 is what divided by 16.
Okay. Let me save you some time. We're not hitting the assert anymore.
Okay.
We're moving on to the next issue.
Vec with capacity plus 2. I'm going to say yes, you can do this.
Yeah, of course.
Yep. Yeah.
Absolutely right. Only in release, though.
What does it do in debug?
In debug, it makes the system allocator very, very sad. But I think if you go down like a few more notches, then the system allocator would just hand you a vast...
Did you try adding more swap?
No, you don't need it. It's virtual memory, right? It's only going to get patient if you actually touch it. Let's talk about loops.
Okay.
So there's no question this time. It's just exposition. So the one neat thing about loops is that if they're simple enough, they can get unrolled. So going from the first block of code to the second block of code, a loop that turns 3 times is just like 3 times the same instruction. And then those instructions that all do the same thing can be collapsed into just one instruction. This is very neat. I just wanted to show you.
It should be divided by 8.
Why did you have to?
Did you ever use Gentoo?
Yeah.
Did you ever fun roll your loops?
No, but I know.
Okay.
I know the flags. One thing, however, that I didn't know and that I learned while researching this is loop unswitching. So what do you see here, James?
So we have an accumulator. So we're passing in a slice of U64s and a bool, and we have an accumulator of 1, and then we're enumerating our iterator. So for each item we have in we multiply by x, which x. So for each item in our iterator, we're multiplying the accumulator by the items we have. But if the Boolean is true, we're also multiplying it by our enumeration position.
Index, yeah. And then there's a black box to prevent like a bunch of code from being eliminated. So the interesting thing here is that there's a conditional inside of the loop, which is wasteful, because if A is false, it's never going to change during the entire loop execution.
So it can't hoist that check up?
It can. It just has to like duplicate the loop.
Yeah.
And then like monomorphize for like true and false,
as you
essentially. Do. And so I even showed you if GitHub CDN, GitHub free CDN works. You can see the 2 different loops as like blocks. The big blocks like left and right, and you can see like the green arrow that just goes around.
I love this visualization.
Yeah, it's from. This episode has a sponsor. I don't know if I can show you because I'm mic'd up. I'm just going to strip, I guess. This episode is sponsored by Compiler Explorer.
Oh, hey, yeah.
I forgot to say it.
Thanks, Matt Godbolt.
Yay, send me the shirt. So nice. Let's play our last game of today. My favorite game.
This is the compiler's favorite game. I'd love to turn that into a Memcpy.
I think we've already talked about this, the two of us, on the podcast. And so I thought I would just test your knowledge, you know? So to start with an easy one, it's just a warm-up. Is this Memcpy we have?
Copy from slice?
Yeah.
Yes.
Yeah?
This is Memcpy.
You know, it's very easy to accidentally not be Memcpy. I'm just giving people time to vote.
But one of them is mutable, which means they can't be the same, so it is Memcpy.
Yeah, that's correct. Also, for the rest of the quiz, there's no like memmove. It's always Memcpy or not Memcpy.
Oh, that's fair.
Yeah. Yes, it is Memcpy. What about this one? Just a manual one. This is a quick fire round, so you have to.
Yes.
Yeah. You sure?
Yes. Yes. Show me the Memcpy.
Yeah, no, it's not.
Wait, why is this one not Memcpy?
Because source can be short, and then it's going to panic. So it could be smart and like insert an assertion
that's fair.
Like this, but it's not.
Now it's Memcpy.
You think?
Source.len is greater than or equal to dest.len, and dest equals source. Yes, this is Memcpy.
Yeah. Yeah.
Yes.
Okay, so now we have this assertion, right? The source is at least the same length as the destination or bigger.
Yep.
Right? And we can make that assertion even stronger. It can be at least length of destination plus 1 or bigger.
When does LLVM give up? I'm going to say no, this is not Memcpy. Because LLVM is very smart in some cases, but then it absolutely gives up in other cases. So I'm going to say no, this is not a Memcpy.
You're right.
But like that's enough to trip up the...
Yeah. That's all it takes. Okay, so some people said it's because then it can actually overflow.
Because it's not proven that source is greater than destination, because it'll make, like, I guess, a separate proof that it's made that dest plus 1, but then it goes, but I can't assume that source is... I guess it doesn't backwards reason far enough about that.
I guess so. Yeah, the best theory I have is that the theta length plus 1 could overflow, and so it's not the same as the previous assertion. I wanted to try it with saturating add, but I didn't have time.
Len can't be greater than I size, but len is a U size, so I think it can't overflow.
I know, but does LLVM know that? I'm not sure.
Maybe LLVM may not.
All right, is this Memcpy?
4i0 source.len.min dest.len. I'm going to say yes, because I've written a lot of code and seen this bound check get elided, which would then turn it into that. So I'm going to say yes, this is a Memcpy.
And you would be right.
Yeah.
It is a Memcpy. All right, now this is the naive Memcpy that we've had earlier, but in reverse.
Ooh, when you said none of them are memmove.
Yeah.
But if they...
Why would it be memmove? They're still not overlapping.
You're right, they're not overlapping. And it's allowed to assume that there's no semantic meaning between this? I want to say it should be able to, but it's not going to be able to, because I feel like that rev's going to screw up the whole thing. But I'm going to put faith in compiler engineers here. I'm going to say this is a Memcpy.
Yes. Yes, James. Yes.
Thank you.
What about this one?
Okay, now we've gone from U8s to U16s. We are asserting that the lens are equal, and we are doing this. I'm going to say yes. I think it's smart enough to realize that that's memcopyable.
Yes, you're right.
Okay.
Yeah, it's just copying twice as many bytes.
Yeah.
Right, easy.
As you do.
What about this one?
For sources has been flattened copied.
Okay, so the reason it's an array of size 2 is because tuples don't have a guaranteed layout.
This is why you were asking on Blue Sky whether that... And I sent you an unsafe code where I'm like, look, you can't do it.
And then I told you to stop watching my socials.
Safe code.
Then I told you to stop watching my socials because I was preparing a surprise for you. Yes. That's what happened. We need an answer.
I'm going to say yes, but I'm...
No, it's not.
Yeah.
Oh, half and half. Nice.
You're right, because
split in the audience.
What would you ask about tuples? Where tuples don't have a guaranteed, but an array has a guaranteed layout.
Yeah. So somewhere in between the guess is flattened. The guess is flattened because it can return a variable number of items. So like the code is probably more gnarly. However, if you use as flattened, which is a method on slices.
Oh.
Yeah. It
Today I learned as flattened. When did we add as flattened to the standard library?
I didn't add it for sure, but
any libs team people in the audience? No.
But then you can just do that, right? It's the much nicer way to write this. How about this one? It looks scary, but it's not.
While let. I'm going to say yes because C tends to do a lot of these loops, so I'm going to guess the pattern matching in LLVM is smart enough to realize this while loop is smart enough. So yes, this is Memcpy.
You have good instinct, James. I like that about you. Yes, it is.
C loves their while. Who needs a for loop? We're just going to while.
Yeah, for sure. What about this one? So it's the same, but the source iterator is copied this time. So instead of being an iterator with item type %U8, or it's just U8.
I'm going to say yes because I'm going to say yes because again, this is just one step away. But I'm going to say yes.
But James, why would I ask if it were yes?
Because
no, it's not Memcpy.
I need to go back to standardized test pattern matching again.
Yes, this is all it takes to break it. My explanation is that now it's values instead of being addresses, so it loses track of where it comes from, and that breaks the Memcpy detection. That's what I think is happening here, but I'm not sure. Is this one?
You know that this is just like a laundry list of someone out there, or who do we have? Petrochenkov, and then who else is an LLVM contributor of okay, this is the laundry list of things we should be smart enough to add as LLVM optimizations.
As always, I'm happy to create work for others.
Well-written work for others.
Thank you.
So we have a byte array source len. We asserted that they're equal, but we do the iterator. I'm actually going to say no, because you did your assert on the original slice before you turn an iterator, and I'm going to assume that's enough to throw it off. So I'm going to say it is not Memcpy.
You're wrong.
Oh.
Well, you're wrong.
For the right reason.
No, you're right. You're right.
I'm right for the wrong reason. Yeah.
That's it. It's not because of the unwrap. If you turn that into an unwrap unchecked with an unsafe block, then it's fine.
I didn't think it was the unwrap. I think it was because you did the assert before you created the iterator, and that makes it far enough away.
No, that's fine.
Oh,
that's fine. Yeah, but I don't really want an unsafe block, so unwrap unchecked is kind of off the table. But it's not smart enough to tell that the source iterator is going to have enough items you can call next. That's too much thinking. I'm very proud of this one. It's an ON square, two-dimensional, diagonal Memcpy.
Yeah.
It's optimized for game dev.
If I just yes, I feel like I'm vaguely remembering all of these little LVM optimizations. I will say no. This is not because it's diagonal.
The duality.
I'm gonna say yes. Yes, it is smart enough.
Yes, final answer.
LVM optimizers has to deal with a lot of very silly C code, so I'm going to say yes. This looks like reasonably silly C code.
Unfortunately, it's not. Now there is a thing which is an LVM research project.
Okay.
And I wish the next slide was if you enable it, then it works. But I couldn't get it working with Rust.
Okay.
So next season. Okay, we're approaching the end here.
Is this Memcpy?
So it's the naive Memcpy. There's no tricks. It's just doing the assignment twice.
But it's doing the assignment twice. Please yes. Please yes. I'm going to say yes, this is Memcpy. I want to believe.
Yes.
Okay,
yes, you're right to believe. Yeah, there's no tricks.
Usually LLVM's pretty... Oh, no. I would say LLVM's very good at aligning that. I'm going to believe that the body of that loop is smart enough that it can realize that there's no spooky going on there because this is Rust. So I'm going to say, yes, this is Memcpy. Rust optimizes better, right? There's no spooky aliasing. Promise?
I'm trying to remember the explanation for this one. I forgot.
No.
But it's not Memcpy. Amanu chased me down and explained to me the thing. Is Amanu in the audience? Does anybody? Yeah. Can you shout the answer? And I'll repeat it.
It is a pass ordering issue with LLVM. That makes sense.
So what's happening is it's running the Memcpy detection before removing the
duplicated unnecessary stores,
and that's why it doesn't actually recognize it.
I just realized Amanu is in the audience, which means I'm going to get the detailed answer for all of these.
Amanu didn't get any sleep last night because I playtested this.
That is the perfect person to...
Amanu's been looking for an explanation for this all night. That's why we have it, so thank you. What about this?
Oh, no. Source...
I'm just making it easier for you and the compiler.
But source is greater than dest, but you do 4. So I'm going to say no, because actually I think your assert is backwards?
No, the assert is fine. No. Nothing's changed about the assert. It's just like...
sure that source is larger than dest, which means that if 4 does... Oh, never mind. Yeah. Okay, I'm going to say yes, this is a memcpy.
Nah. For the same reason, I think, as the previous one.
I'm learning that I'm not good at lightning code review is actually what I'm learning here.
What about this one?
Wait, what? Oh, what? Yeah.
Yo?
Yeah.
That's not an answer.
We said ordering of passes, because the first one is not needed, so it gets deleted. No, it's not. I think it's the same pass ordering problem.
No, you're wrong. This one is Memcpy. Well, thanks for playing, everyone. I think we're running a little long, so we have to move on to the leaderboard, and I really hope that, yeah, wow.
All right, who's strong meerkat? That's fair.
Could be someone on the
is it Amu? Congrats to Amu for winning this.
Well, I think that's it for us.
Excellent.
Did you like the quiz?
Love is a strong word, but
I said like.
Always happy to be here with you. Thank you, everyone.
Thank you. You too. Yeah, thanks.
Round of applause.